Yes? No? Okay. All right. If there are no questions, let's just move on to the next topic, which is the feed-forward neural networks. Now, the differentiation is the two things that are happening here. If you look at we're going from one neuron to a network. So now we're going to look into how, when you combine the neurons together, how do they function? Now, when I say how do they function, there will be a little bit of math. I'm not going into too much detail unless someone really want to go into the detail. We look into two things. We look into the representation, that how would you represent when you have multiple neurons and they are in multiple layers, and then what would be a matrix representation look like. Because if you think about it, when you have vectors and then vectors are multiple vectors, basically we are talking the matrices, and we'll see how converting it into matrix multiplication or matrix mathematics make the calculations a lot easier. So that's what we will do. We will not go into too much detail, but we will do a little bit of calculation so that you get a feeling of how exactly these things function. Feed forward basically means that we will look into the network in its one side of the movement. One of you asked the question that why we have the backward arrows. Those backward arrows were representing back propagation for in the period when we are discussing this session, the feed-forward neural network, at least for the next 30-40 minutes, we are not going to look into back propagation. We are only going to understand the movement from input to the output. The whole idea, as I mentioned, is twofold. One is that how do you represent when you have more than one neurons and more than one layers? And then two, can the matrix multiplication or matrix mathematics help us? So those are the two focuses here. So this is one way of looking at it. You have now multiple neurons and two layers, right? You have inputs coming in here. They're going to first hidden unit. The hidden unit means that these units, the neurons in these units, are neither receiving the input from the external world, nor they are producing the output to the external world. There's an input layer. The input layer doesn't get counted when you say that how many layers are there in your neural network. Input layer is never counted. So this network will be called one hidden and one output layer. That's the neural network here. Now, if you notice that, now imagine what we learned about one neuron and try to fit the understanding here. Hidden layer, output layers. Y represent the output of a single neuron. So y1 to yn basically says that the output of the neuron, the yth neuron. The last one, if you notice, says yn2. That says that this is the output of y, output of the nth neuron in second layer. The first layer is hidden, the second layer is output layer. So understand the representation, how exactly we are saying. H1 is the first hidden neuron, or H2 is the second, so on and so forth. Hn1, nth hidden neuron in the first layer. Okay? W represents the weights, U represent the weights for the hidden layers. B is a bias, and the bias is introduced, if you notice that, in each of the hidden layer. The bias is added to the input, so it's not in the input neurons, it's just added to the first output or first hidden layer. Is that point clear? So if you say, someone says that YNI, so that's the output of nth neuron in the ith layer. Yeah? It's clear? So if we move on to that, what are we doing here? The calculation in each neuron is this. Weights multiplied by inputs, bias added to it. The output of that is passed on to activation function, and which results in an output. That's what we are saying. W is a vector, B is a scalar, input layer is vector X of whatever the dimension is, let's say n. That's what you end up being. a single number after this calculation. And I mentioned that we don't count the input layer. If you think about it, this represents, a single node represents a binary logistic regression. Now, what is regression? A couple of you had already mentioned, you know this. So what we were talking here is nothing but a regression analysis. Given the age and height, if you fit a function, then you can approximate that at the age, say 11, what would be the height? And you will get some height based on whatever the learning data or training data I've used, right? Binary means that it would give you either a 0 or a 1 answer, not like I gave it, because we are passing the output into a activation function, which is a binary or a linear activation function to give a 0 and 1 answer. So a single neuron represents, a one layer network can depict a binary logistic regression. Think of it, what I'm saying here. A single neuron can be trained to perform a logistic regression analysis which has a single output, binary output. Are you with me so far? So, what I'm saying here, a one layer network, a single neuron can be trained to differentiate, let's say, between a bird and an animal. Given the right amount of learning, it can be trained to distinguish between, because any binary output, I mean bird and the animal is one way, but any binary output, right? Is that point clear? Because all it's going to do is to find out the discrimination function which tells it whether the input is this side or that side. Understand, it has no idea what bird is, what animal is. All it knows whether it for this side of the curve or this side of the curve. So same way, why the mathematics of curves are important? Any natural phenomena, here we are trying to distinguish between a bird and an animal. The model doesn't know what bird is, what animal is. It's just been trained to identify that here is the discrimination function, whether an input falls on this side or this side. It's also not going to tell you bird or animal, it's going to tell you 0 or 1. You need to interpret what 0 is and what 1 is. Good? Unfortunately, the word is not always that simple, right? The binary is not always. You may need to differentiate whether it's an animal with 2 legs or 4 legs, or a bird which flies, a bird which doesn't fly, whatever the case may be, right? So you may need a function that might require more than 2 outputs. Okay, so let's introduce a new function here. If you have what is known as multinomic logistic regression. Multinomic basically means that you're not just limiting your output to a binary, but it can have multiple different possible values. What you have now is called a multinomic logistic regression, still a one layer network. The only difference here is that the output layer is not one single neuron, but a range of neurons, depending on how many different options are there. And then what is happening here now, you're saying that my neurons will tell me what's the possibility of each of these potential values. So for example, let's say you're trying to train a network which can differentiate between, let's say, a cat and a dog, and let's say a lion. So now it will say that my multinomic logistic regression neural network will have 3 output neurons, and my network will be trained to give me probabilities of one picture coming in to say that what is the probability that this particular picture is of a cat or a dog or a lion. Probabilistic output here. So that's what's going to happen. Basic remains the same. You have input layer, which are scalars, weights are matrices, there is a bias. Function now changes. Instead of a binary function, we have what is called as a softmax function. What is softmax function doing? instead of giving you a 0 and 1 answer, which is what our earlier sigmoid, 10H or ReLU function were doing, a softmax function gives you probabilities. The underlying math remains the same if you think about it. This was the calculation earlier, right? We talked about probabilities. I think on the day 1 you have the number of observations possible and then the choice of or number of time the desired occurrence is happening. So if there are probabilities, Zk is a probability of the kth neuron or kth value 1, 2, 3, you take the exponent of that particular probability and summation of all the other probabilities, that gives you the answer. So if you apply that to the roll of a dice, 6 possibilities, each possibility is equal. If the dice is not necessarily rigged, then every possibility is 1 by 6. You're doing exactly the same thing here. 1 over the summation of all possible values. So that's what the softmax function does. So what we are saying here is that we are replacing the activation function from a binary result to a probabilistic output. And that softmax function is described by the exponent of the Zi, which is the actual output, and the sum total of the outputs. The neuron is still producing the sum, the same calculation, weights multiplied by input plus the bias. That number is sent to a softmax function or softmax layer, which then turns that number into a probability. Is that clear? The basic neuron is still doing the same calculation. Y, which is an activation function sigma, W multiplied by X plus B. Output of this is sent to a softmax layer. You will learn some more terms and or more type of layers as we go along. And then basically that layer is converting this individual number of a binary into a probability using a softmax function. We're not going to drill any more down on the mathematics, just explain how exactly it works. So don't be afraid of that we're going too much in the mathematics. The only one other mathematics that we will come and talk about in the next hour is partial differentiation. So we go one more step there, and just because so that you understand and I'm not going to go into too much math there, just give you an intuition of why partial differentiation is important. Now, why this is important is because the back propagation is the most important part of this entire development. Without back propagation or efficiently computing back propagation, none of this was possible. So even if you don't get the entire math, try to understand the intuition behind it, right? That's the important point. Okay, so what is going on here is that same calculation, you're getting the output here. It could be a rectified linear unit, 10H, sigmoid, doesn't matter, it's a single number, which then goes into an output layer. That output layer, in the case of a scalar output, which is just one value, could be a sigmoid function or any other function. But if you have a multinomic output, okay, and the next example is a 2-layer network with a scalar output. So let's just try to understand this here. So this is a scalar output, single number. This is multi-layer output. Now here what is happening, if you think about it, again in nomenclature, the weights matrices here, the weight of the jth neuron due to ith input. So the intuition here that you need to understand is that all of these things, the W's and B's and X's and Y's, are going to become matrices. A, because there are a number of neurons at each layer, and then there are multiple layers. The nomenclature is important because I want you to have intuition, and for having the intuition you need to understand how we are representing these, because when we start talking about back propagation, which is the most difficult one to comprehend without actually coding it, but I do not want to go to the level of coding here, but you get the basic idea or intuition. So from single neuron we went to the layers, and then when we have the layers, this was the weights were here like a vector. Those vectors will become a matrix here, and each Wji element of the matrix says that the weight for the jth neuron from the ith neuron, weight from the neuron in the jth layer due to the output of the neuron in the ith layer. That's what is happening here. Make sense? So what we are doing here, this is a two-layer network with scalar output. When we say scalar output, there is only one output, slightly simpler. When you have a softmax output, that's where you have the softmax function and it has more than one potential output and you get the probabilities. Let's take the example, this one, two-layer network, and see how the notation looks like. So xi's, which is the input, this is a vector. The bias has B1, 1. The weight network is very simple. In the first one, that weight 1 is the weight based on the first neuron from the first layer. The equation becomes very simple here. We have seen this, W multiplied by the input multiplied by the bias. The input here is A0, which is basically the bias or fixed input. At the next point, the A1 becomes function G of whatever is the output from this layer. So keep this in mind. We're going to talk about this when we are looking at back propagation. At each level, we have a function. At this level, it will be function of the output. Is that point clear? So X is the input. At the layer 1, we are saying that f of X. At the layer 2, G of f of X, because every time you are multiplying it by the weight, adding the bias, and then passing it to the activation function. So if you have two layers, you have two functions, G of f of X, and a final softmax function to give you the result. So this is what's showing, the G of Z of whatever the activation function. Here it becomes G of Z of second layer. This is the first layer, this is the second layer. Same function, this is the weight from the second layer, input from the first layer, the bias on the second layer, and then it gets computed in the approximate way. So think about it, like modern foundation models have billions of parameters. Those parameters are nothing but the same biases and weights. That's all the neural networks are doing. ChatGPT. So if you think about it, what is the secret sauce of these things? These weights and biases that they have learned. That's what is all. If you have seen the OpenAI, for example, they are publishing the weights and biases used in their network, right? And a commercial company, when they have trained a model, they are not publishing the weights and biases, because if you get their weights and biases, you basically get their model. So anyway, when we have billions of parameters, then you have all of these numbers all over the place. But the basic remains the same. That's all it is. It's just the number of neurons that we have. Make sense? Now, I'm going to take one more approach here. So this, we have seen this picture before, right? Single neuron, inputs, fixed bias, and then summation, activation function, and a single output. If you take that and use it into multi-layer notation, this is what it's going to look like. So y prime is the computed function in the second layer, which is basically G multiplied by Z. Z is the output of the prior layer as weights multiplied by the values coming in the hidden layer plus bias, which is again a function of G multiplied to Z, where Z1 is the very first layer of the input. You just basically increasing it one layer at a time. Does that make sense? Intuitively, because we are not asking you to write the equations here or write the code or compute it, right? But I'll say one thing. Earlier I mentioned that go through the exclusive OR example. If you do the calculation, you will get a feeling of how exactly weights and biases work, and they do produce the right result if you have the right weights and biases. If you want to extend that example, how the exclusive OR was implemented, you can try following this way with the 2 level of functionality. So try doing the hand calculation, it will create intuition for you. Okay? Here I'm just trying to give you the nomenclature. So literally what is happening then, if you think about it, where we are going with it. In terms of the representation, we have this calculation where we are saying you give the input here and it goes to the next level, you go to the next level, you go to the next level. If you've done any amount of programming, you know that now once we know how to do something, now we need to do the optimization of that algorithm so that the calculation becomes faster. So really speaking, what's happening here, as you have the input moves from multiple layers, this is the kind of calculation that is happening. So 1 to n, that's the number of input neurons that you have. You calculate the z, which is a function at the output, which is weights multiplied by whatever the input values are, adding the weights, pass it through the activation function, and that gives you the output. This could be a single value as a scalar value, or it could be a multinomic, which is a vector in itself. That is just happening at each layer if you think about it. So that's the simple calculation that's happening. Now if you're trying to optimize this calculation, what should we do? Now one thing that people realize that, why do we need to keep this separate function? We probably don't need to. Let's say that this is also an input x0, then this entire thing is just this calculation. If you see this, the original value is 1 here and there is a bias value which needs to be learned. So if you want to simplify the calculation, let's remove this, make this part of the x itself. This becomes x0 or weight 0. So one of the way we can simplify this calculation is by doing this. Add a dummy node to each layer, its weight will be the bias, because really speaking there's no difference. We said learning is learning or finding out weights and bias. The only simple change that we are doing here is that rather than having bias as a separate term, let's assume that it's a dummy node with a value of 1. We will discover the weights, we will discover the biases as well. Weight W0 will be the bias. So now instead of this, we have simplified it to just this. Nothing much has changed, right? Everyone's clear, right? If you think about it, when we had B as a bias, the input of 1 was hidden. Now we made it explicit, and then we said that now our calculation is slightly simpler. Our input is this, x0 by default is always 1, but we don't care about that, we just say it's a vector, and now our calculation is sigma of W multiplied by X. That clear? Okay. And then the activation function is whatever the number of neurons you have, you just sum that over. Okay, let me ask you one question. It doesn't necessarily, I don't have it in the slides, but how many of you are familiar with matrix multiplication? Okay, how does the matrix multiplication function? Yeah.
Row and second matrix as a column.
Right. So it's basically a multiplication where the column of the first one are added to the rows of the multiplied by the rows of the second one, and then basically it adds up and gives you a number here, right? Is this the multiplication that we are doing there? Yes? What makes you think so? Sorry?
As an input, we are passing the matrix, and we are doing the calculation.
No, which one is a matrix and which one is a vector?
It's a singular matrix here. You can see x1, x2, and this input. Like
So x1, x2 is a single neuron value, x is a vector,
yes, yes.
w is a matrix.
Both are matrix. But
Okay.
there's
Well, okay, fine. Both are metrics, but the W would depend on how many layers you have.
it can be multiple, but here it's written single.
Okay, so let's try to understand what we are trying to do here is we are trying to calculate this number, right? Summation of Wji xi. This indicates that this is a multi-dimensional or at least a two-dimensional. This is a vector, right? Okay, so what I'm trying to say that this is not a true matrix multiplication that is referred here. It's an element-wise multiplication, slightly different, because what is going to happen if you think about it, let's say you had a vector here which is n into 1. Yeah? First of all, to do the matrix multiplication, you need something which has n here. Let's say, fine, n are here because every time the same number of nodes and there are m layers. This multiplication will result into what? An m by 1 result. Right? But that's not what we want. We want an m by n result here. So this is not a true matrix multiplication. There is another product called Hadamard product, which is the element-wise multiplication of two matrices. And if you have A, it's represented, I believe, like this. That is the calculation that is used in the neural networks. I'm not going into too much detail. The only point I wanted to make is that we removed the +1, convert it into the a matrix, and then basically have the element-wise multiplication to do this calculation, right? That's what we are simply trying to do here. We're trying to simplify and optimize so that we can do it a lot quicker. Okay. Makes it? Get it? I don't know why this one is not showing a picture, but let's go with it for now. So we learned that if you add a hidden layer to logistic regression, you can actually see the nonlinear interaction between features. Is that point clear? This is how we implemented the exclusive OR. Without having a hidden unit, we couldn't do the exclusive OR. We could only do the linear functions, which were the AND and OR. This is what I asked you to manually go through and see the weights and biases can be learned so that you can implement a exclusive OR unit using one hidden layer. This is what the hidden layer allows you to do. May or may not improve the performance. So if you think about it, the one layer without hidden layer, you are trying to do, you get the logistic regression. If you have a hidden layer, it's a two-layer feed-forward network, and you can actually do the non-linear interactions as well. Is that clear? At least from the intuition perspective. So if you think about it, what we did in the last hour or so, first is that we established that a neuron can be used to learn something. That something was discrimination. We said that a linear function or linear activation function can be used to discriminate between two outputs, cats and dogs, or whatever the case may be. The neuron does not know cat or dog. All it will give you 0 or 1. You interpret how the zeros and ones are. Then we said that if we want to claim that this is a fundamental building block which would let us do anything we want with it, the intuition there was that can it do AND OR and exclusive OR gates? Because if that can work, then because those gates can be used to build any computer program, we should be able to do any learning here. Very quickly we learned that we can do AND and OR gates, but not the exclusive OR gates. Then we realized that if we add a hidden layer, even if we are using the linear activation function, we can have the one hidden layer or a two-layer feed-forward network can actually also implement exclusive OR. That's exactly what I'm saying here. In between that point and here, what we said that can we simplify the calculation. To do that, we eliminated the bias term, treated as the x0 or the 0th input, and then said that let's try to see if we can use the matrix calculations. Then we realized that we can't use the regular matrix multiplication formula because it requires two matrices and it converts it into a one vector result. So we said we're going to use the element-wise multiplication to do the calculation. The whole idea still remains same, that we are trying to introduce a hidden layer using linear activation function, learn the non-linear behavior. How did we do that, if you remember? What I said that we took a two-dimensional observation, try to bring a hidden higher dimension where a single linear separable function was able to separate something which cannot be separated in two dimensions. Now that intuition is also very important when we go into the language models. What did we learn here? Something that cannot be separated in any given dimension. The example we saw in two dimensions. If you somehow convert it into a higher dimension, you can still use a linear separable function to separate these things out. That's an intuition, right? We have to test it out. Is it true or is it not true? So far with me? The only other thing that we did is that how do we optimize or improve the calculations, which is what we did in terms of the matrix one. Okay. All good so far? So the real thing that comes from is the ability to learn features from the data, which is what our goal is here. And one of the things that we have learned is that we may sometime need to take our data and represent it in a higher dimension, because that makes it easy to differentiate between the data that we have. There's the two new terms here introduced. We're going to talk about them. One is classification and one is called embeddings. Right? We'll come across that, but let me just give a little bit of an idea here. When we are changing the dimension of your underlying data set, so you started with a two-dimensional data point. We're not going to use the word point anymore in higher dimensions. We actually don't even know. What we are saying is that we call it embedding. So the two-dimensional point becomes an embedding into a higher dimensional space. Why the intuition is important? Because we can't differentiate or we can't depict a higher dimensional space in a two-dimensional screen or things like that. So you need to kind of visualize intuitively of what it could be. We do not even have mathematics to sometimes describe. If you look at the large language models, they are using anywhere between 4K to 8K dimensions at any given point in time. So visualizing it is very difficult. So make sure that you have the intuition of what is going on here, which is very simple if you think about it from a two-dimensional example. Exclusive OR function that cannot be linearly separable in two dimensions can be defined in three dimension in a way so that a linear separator can separate it. That's the basic intuition. Okay? So just an example in the next screen of what I said. We're going to not be able to fully probably comprehend. It will take about an hour before we reach there, but let's just see what we are saying here. A language model would be something like this. You will start with a statement. That statement would be converted into embedding into some higher dimensional space. Those higher dimensional space will actually have the same mathematic that we saw, and then passing through one or more hidden layers will result into a sigmoid or an output layer. That output layer will tell you whatever the goal is. If the goal is to find out the sentiment of the input statement is either positive or negative, you have a binary output. So a sigmoid function or a ReLU function or a 10H function. If you were trying to get the multinomic output, you will have a softmax function there, right? So basically what this example is showing, I mean obviously it looks a lot more complicated than what we have seen so far, is just transfer this into what the large language model, or let's even take out the large out, what a language model is doing. If you think about this, what this language model is trying to do, given a sentence or a statement, it is trying to find out, is the sentence representing a positive sentiment or a negative sentiment? So it's learning and then telling you whether it's discovering positive sentiment or a negative sentiment. That's exactly what's going on here by exactly doing the same things that we just talked about. Hidden layer, the embeddings, because we are trying to use the linear functions as much as we can, because that simplifies the calculation. One or two or more hidden layers, and finally you get the answer what they are looking for. Is it positive statement or a negative statement? That's what the language model is doing. So far so good? All right. Just make sure that you ask the question if you have any. I'm just giving an example here, and we're going to take a break for if you have ask a question as well. This was a single output. If you have a multiple output, the only thing that's changing is that you're basically using a softmax function. Let's call it a softmax layer, where you have multiple choices of two options, and then it ends up into a probability. Which one has a higher probability? Which one has a less probability? Okay. So, any questions? Intuitively, if you think about what we have done, we started with a neuron, we looked at it, what it can do, what it cannot do, like exclusive OR. Then we said if we introduce a hidden unit or a hidden layer, we can actually do the exclusive OR as well. Then what we did after that, we said fine, but it is still giving us one output. What if we need to have multiple outputs? So we introduced a new kind of function called softmax, or a softmax layer, where we said that now we can actually take the activation function in a way so that it is giving us probabilistic inferences. Okay? And then I showed you one example just like that, in the way, like asking you to trust that this is how, if you are trying to build a system that can learn about the sentiments of an input sentence, this is roughly it will look like. Okay? Now, if you were to say how exactly it's going to work, it will have to learn. Learning is finding out these weights and biases. Learning will happen through the labeled supervised learning. You need to give it, let's say, 10 examples, that this has a positive sentiment, this sentence has a negative sentiment, and then based on that learning. Now, I just gave a random example of 10, 100, 1,000, I don't know. More learning it does, more the discrimination function will become. Right? So, basically, if we go from there, if you guys have no questions, we're going to move on to training neural nets, because that's what is the key thing. Before you get to it, then yes. Sorry, say it again. Yeah. No, every node is exactly same.
Then if we are sending one input in a multiple node, so if we are sending in three places, it can be same output, right?
Okay. All right. So let's make sure that we intuitively get it right. So input is this, which is a vector. Right? This vector input is going into the neurons, and they're going into the layers. So the basic fundamental setup is same. This is input, but then its output becomes the input to the next layer till it reaches the output layer. So the basic calculation is exactly same everywhere. You have input, you have biases, you have weights. You have the summation, and the summation goes to an activation function. The only thing that can differ between the layers is that different activation functions can be used. So something that I've not introduced so far, but eventually we will. You may say that there is a pooling layer, then there is a softmax layer, then there might be another layer called convolutional layer, for example. So if you go back to what I originally said, what is our goal here? To build intelligent system. How will we build intelligent system? Two parts. A, the representation or organization of the network. B, learning, which is the weights and biases. So weights and biases will be learned. We'll take the example of learning as we move into the next section. The architecture will be the research. So some activity will require you to have the softmax layers, some will require convolutional layers, convolutional network, recurrent network, all kind of architectures based on what is required. But every single of these neurons are doing exact same thing, what we have seen so far.
Okay.
Weights multiplied by the input, add the bias, sum that up, pass it to an activation function, period. That's all that's happening.
Okay, we are writing the hidden layer, right? So hidden layer, what it does, it take the input and convert in some simpler things. You told, right? Simpler.
Okay. The hidden layer is called hidden layer just because that there is no input going to it directly and no output. It's basically taking the output of one layer and using it as an input and giving it to another layer. That's the only concept of hidden layer, right?
Okay.
What does it do is more or less what you're describing, in the sense that it converts the data into features. What we do not know at this point in time, how exactly, if you have heard about the large language models, how do they work? We don't know for sure. Especially the large model which have millions of neurons, people are still trying to figure out what each layer is discovering. What we know for sure, it's discovering features, some features. They're not exactly what we think they are because they are differentiating functions in a higher dimension space, if that helps. Yeah.
Okay. One very important thing. In OneNote, if you wrote something written for fractional, like some we are doing fractional and some calculation doing like IEEE 235 75, that decimal something we are doing, then it can become very harsh for the system or harsh for the network. That represent if you're doing any calculation. First thing, and second thing, you shown
Sorry, I didn't get your point.
like here we are doing some calculation here, and we have some input which is like IEEE 1 notation are there, double precision notation we are doing solving.
Okay. So you're saying, can the weights and biases be in the double precision notification?
Yes.
Okay. So we are going into now in the kind of optimizing what we are trying to do. Okay. So a simple answer is that most of these things avoid the double precision arithmetic because that's not necessarily a right way of doing it, and we want the fast calculations. Having said that, we do want that level of differentiation. Why? These models require GPU for training because the GPU does the floating point arithmetic, not the double precision, but floating point arithmetic. That's why the GPUs are needed. GPUs are needed to do exactly these matrix calculations which are using the floating point numbers basically, or higher precision numbers.
Okay. One more thing.
Yeah.
If you go to the next slide, one more. Yes, this one. We are sending here some the result is in the output. We are following the, if we are getting any output, like we are changing the language, so we are following that here for the Noam Chomsky, that grammar rule 0, 1, 2, 3.
Don't even take it there. Are you describing a situation where you are translating from one language to the other language? Is that what you're saying?
Yes.
Okay, we are not there yet.
Okay.
We're not looking at this, and I said that I have introduced this here. Right now we are understanding the basic calculation, and what I have told you is that we looked at one neuron, then we said that how we can combine the neurons. I think your first question was very relevant, that calculation is not different. Doesn't matter what layer it is, doesn't matter what the location is, the calculation remains same. Now this slide has a lot more. This slide defines one specific type of problem, which was the finding out the sentiment analysis as a classification, positive or negative. Now what you're asking about is that can we use this from English to French translation? The network will probably look like differently. Now, we're not going that far out there. I mean, as a class, we're not ready to talk about these kind of problems. We are only learning about how the simple stuff happens, how does the neuron function, how do we combine a hidden layer, and understanding the mathematics behind it. Okay? The only thing that you've learned, and I mentioned here, is that if you want, this is giving you a binary answer, positive or negative. If you replace this from a softmax layer, you will have a probabilistic answer where there could be 10 different answers, 100 different answers. How do we combine these neurons? The methods is dictated by what is the problem you're trying to solve, right? But we're not going there yet. But what I said is that two things we need to learn: what structure, what functions, and how does the learning happen. All right, any other question before we move on to this? Okay, then no question, then let's just go into training neural nets. So, I've said it so many times, what does training neural net means? Come on, that's easy. I've said it like 5 times already. So the training neural nets means, come on guys, someone, given labeled data, supervised learning, let the network learn the right weights and biases. That's what the learning is all about. Yeah? Simple. I mean, a few things. If you're ever going to claim that you know the machine learning, learn these few sentences. This is a recall sentence. That what is learning? Okay, learning is finding out the right weights and biases in a supervised manner. Okay, so what is going on here? You provide a training instance, and then because you know the output, you see that are we giving it the right weights and biases. And by the way, just make sure that you do work out by hand the exclusive OR and an OR, because that will give you the importance of weights and biases, and then it will give you intuition of what learning is happening. And you will realize that if you change the weights and biases for AND and OR, you will see that it's not giving you the right answer. So what I want you to intuitively understand that any learning is just about finding the right weights and biases. That's it. So try to get that intuition, because once you get that intuitively, you have actually learned the basic building block of machine learning. Beyond that, it's about how do you combine that basic units in different architectures and different functions to make it do what you want it to do. All right, so training a 2-layer network, you provide some inputs. It is trying to find out all the weights, W's and U's basically. In a forward pass, it will calculate whatever the output is and produce an output Y prime or Y caret. That may be different from what you think it should be. So I have mentioned this all along, but I'm just kind of now talking in terms of training so that you figure out. If this is the actual answer, this is the output. What needs to happen? Tell me. I've said it like half a dozen times already. You need to change the weights until the time then the output matches with what it should be. Right? So you calculate the loss function, the difference between the actual answer and what your system is producing. The learning is not complete. Then you do a backward pass. One of you asked why we have the arrows going both sides. The backward pass is adjusting the weights. How much? Finding out the rate of change, adjust it in the opposite direction, and then basically continue the process till you match with the exact answer. Does that sound like an algorithm? It is, because that's how the learning is functioning. For every training data, X and Y, X is the input, Y is the desired output. You run the forward computation, figure out the Y prime. If the Y prime is same as Y, learning is complete. If not, you run the backward computation where you change the update, the weights. For each node, compute the loss, and then take the weight, update the weight, and then do it again, over and over again. You run this in a loop till the point where the network has learned enough to produce the right answer for all your training data. Make sense? Okay, I think I'll need the connection here for the battery. Yesterday somebody had it. Yeah, you had it? So what we are saying here is that we can train a 2-layer network. You can actually generalize it to make it a number of layers or whatever the case may be. Right? Is that point clear? Okay. Now one more thing in parallel that we have been talking about, how to simplify the calculation, because one of the things, if you are a computer programmer or computer software developer, you're always trying to simplify the calculation. So one of the things we are trying to do is to simplify is that, can we find out a simpler loss function, right? And when we say simplify, we are trying to simplify so that the best case scenario, worst case and average case scenarios are not quadratic functions. We all know that, right? In the sense that if you are, let's say, doing a matrix multiplication, if you have an algorithm that computes the worst case behavior or average behavior order of n square, right? That is not a good algorithm because, not this, C-type. Oh yeah, it is a C-type, yeah. Yeah. Okay. Bear with me. This is the one. Yeah, hold on. No, this is fine, but this is, yeah. Yeah. Okay. Sorry, what was I talking about? Yeah, we were trying to simplify. If you have an algorithm which runs in order of n square, you try to discover something which runs order of n log n. N log n is better than n square, right? So one other thing that we are trying to always find out is that if you want to keep it, make it really useful, we want to reduce the complexity of the algorithm, the time complexity and space complexity here. So one of the ways to do this is to see that the loss function that we have here somewhere, can we simplify the log function, that it doesn't require an order of n square computation. So what we have done is that, in a way, that there is a loss function called cross entropy loss for logistic regression, which basically involves simply saying that if you take the cross entropy loss is defined as that the loss between a difference between the two is actually computing the log space. So log space is that rather than computing the simple difference, we are saying that log of probability of y given x has already happened, and then when you start differentiating it, this becomes y log y. Again, this is a differentiation of log function. Does anyone know that? I mean, I'm just assuming a few things here. Make sure that you can refresh your differentiation. So I actually jumped a little bit here. So we talked about differentiation of function. Then you need to think about how do you differentiate a function if it has more than one terms. So if you go back to like 3x plus sine x or something of that nature, or the function of function, because if you remember that I said is f of g of x. So what you have is something called chain rule. And then how do you differentiate a function if it is log? So what we are trying to do here is to simplify the calculation by saying that our cross entropy for logistic regression is negative of the log probability of y given x. So really speaking, I mean, this is a pretty complex thing. There's one more thing here. It's called Bayesian probability. How many of you have termed the Bayesian probability? Actually, I should have introduced a bit more math here, but not going too much in the detail. Does anyone know Bayesian probability? Sorry? Yeah. Okay, what is it? Okay, sorry, what were you saying in the back? Same thing, okay. You've heard about it, but you don't know what it is. Alright, so there are two things here. So if you think about it, let's say you have a jar which has a red and a blue ball, Okay? So, one is to say that if you take, let's say it has 100 balls, let's say it has 30 red and 70 blue balls. If you take out one ball, what's the probability that it's going to be a blue ball? Sorry? Right, so a possibility here would be because 1 out of 30 on the top and 1 out of 100 down there. So roughly that's a probability. Now let's say the first one was blue. What's the probability that the second one will be blue? Okay, all right, let's. Right, so basically what we are saying here is that that's where the Bayesian rule comes in. The Bayes rule simply says that it's a conditional probability. Given what you know about the state, how you find the probability. If the first ball was blue, the probability of second blue ball is going to be different if the first ball was red than the probability of the blue ball. And there is a formula for it. I'm not going any further in the detail. I just wanted to give you a little bit of an intuition what's the Bayesian probability is. Bayesian probability is that finding out the probability of the second ball being blue if you know what the first ball was. So there are three cases here. Finding out the probability of second ball being blue without knowing what the first ball is different from if you knew what the first ball was, what's the probability of second ball being blue. Bayesian formula or Bayesian probability talks about given what you know about the prior incident, what's the next one. This is the Bayesian formula, probability of y provided x has already happened. If you take the negative log of that, that becomes a good cross entropy loss, which is called cross entropy loss, as a loss function. The benefit of using the cross entropy loss as a loss function so that its calculation becomes a lot easier actually. It doesn't involve the matrix multiplication. It has simple logs, and then when we learn about the back propagation, we'll see how the calculation of this loss formula becomes a lot easier and it helps us. Alright, make sense? Yeah? Okay. How did we reach here? Now we need to see the differentiation of this log function. So differentiation of a log function operates, this is basically expansion form of this, and then once we need to differentiate, we'll see how we want to differentiate this function as well. Okay. Still the intuition, okay? What we are saying, we are not going into too much deep in the math, just intuitively understand what is going on. How many of you know partial differentiation or recollect partial differentiation? That's the symbol down there of partial differentiation. Does anyone know what partial differentiation is? Alright, again, I'm not testing you there, but let's just get the basic intuition, and it's important because otherwise you won't understand what exactly is going on here. So, what did we define as differentiation? That we did this morning itself. Does anyone remember? Sorry? Right. So if you have a function which is f of x, which is y, the differentiation dy, let me do it, df of x is actually dy over dx. So change in y for each unit change of x, that's dy dx. What if the y is z equal to f of x and y? How do you differentiate? Now you have two possibilities. Change in z for one unit change in x, keeping y as constant. So partial derivatives are always for functions which are having more than one independent variables. So partial differentiation of a function with respect to one of the independent variable is basically saying that what's the rate of change in z when x changes 1 keeping y as constant, right? So when we said that the learning is weights and biases, so we at least have those two terms, and then you also have input from the prior layer, so at least 3 terms. So we will need to differentiate or have partial derivatives with respect to each of these things separately. So we will end up doing this to some extent. Alright, now this one talks about more or less the same thing. Loss functions, you need to calculate the loss functions with respect to weights. You also need to do with respect to the biases also, but as simple as that. You have f of x prime, which is really the output that you got with certain amount of weights. This is the actual output. You calculate the loss functions. You need to calculate the partial derivatives with respect to the weight to find out how much weights need to change. So you do this over and over. At the t plus 1 iteration, the weight will become the weight from the last iteration. Now there's another term introduced here. I'll come to it in a second. Negative of the change in the loss function. Yeah? So far with me? Except this new term. That new term, I'll talk about it in a little bit. Is that point clear? For logistic regression, it's a lot simpler because this is exactly what you're doing. This was much simpler case. As you go in a higher level, it becomes more and more partial derivative across multiple or multinomic functions. Is that part clear intuitively at least? Yeah? Keep that symbol in mind. Does anyone know what that symbol is called? Sorry? Yes. Okay. It's a learning rate. Eta, it's a learning rate basically. What is learning rate if you know that far out?
Y minus y squared.
Okay. My question was that like why do we need it? What is learning rate? Not always necessarily. Okay, we'll reach there. It's a little too early, but yes, she's right. Because I have not introduced it, so I'm saying that just assume that it's there. Why is it there? Why do we need it? Intuitively, we'll learn about it in a little bit. So this is exactly what we are doing, is that you're training the neural network. You're trying to figure out that the weights, and they need to be updated. You need the partial derivatives. If you choose the loss function correctly, the calculation of partial derivatives will become computationally easier. That's what we are trying to do. Chain rule was already used there. I mean, assume that how many of you understand the chain rule, right? You understand the chain rule? The function of a function of a function, etc. And when you're trying to differentiate it, that's how the chain rule goes. If the function is this, u of v of x, you're trying to do df by dx, is basically saying that you do the du over dv because that's the function, and then dv over dx. These two needs to be calculated separately, and then you can find out the overall function, right? That's what the input is, just the example that's going in here. Loss of y over z over weight, derivative of the loss, derivative of the activation, derivative of the weighted sum. So those are the 3 things that you will need to be calculating at each step while the learning is happening, right? Yeah. So from intuition perspective, are you all clear what is involved in learning? At each layer, you're calculating partial derivatives of each of these things. The weights, the loss, and then the activation function, which is the output of prior layer. So far so good? Okay. I'll say one more time. Try do the hand thing for the AND or an exclusive OR, because that will give you an idea of how you are changing. It's very simple because they're all linear. You can hand calculate and see how exactly the weights and biases get adjusted. The slide already has the final value, but I would suggest that start with the different weights assigned to them and then see if the learning does happen. and you should see that the learning does happen. Okay? All right. Any questions before we move on to something else? All right. If not, the backward differentiation, which is what we have been doing all along. Now, what are we trying to do here? Intuitively, we understood that we need to calculate the differentiation of the loss function and use that to change the weights. What I'm focused now in the next maybe 15-20 minutes is how to do it efficiently, and that's where the computation graph and the backward differentiation comes in, the backward rules here. Okay, so what are we trying to do here? I've said this like so many different times, but let's just repeat it again because that's the basic stuff that you need to remember. When we are training, we are taking the derivative of the loss with respect to each weight and then adjust the weight accordingly. Now, this can be computed only at the very end of the network. Once you've calculated, then it needs to go back. That solution is called back propagation. The back propagation, and this is a pretty old one, 1986, but it was only in the early 2000s that Geoffrey Hinton figured out that we can use back propagation to do the learning, and it will be making the network learn much faster, because otherwise it was a problematic thing. What it does, it relies on computation graph. So literally what we are now saying is that our neural network becomes a kind of a computation graph, which when you apply backward differentiation, act as back propagation, which means that it's basically let you calculate the derivatives and update the graphs much faster. Okay? Has anyone heard the term before, computation graph? Yes, no, maybe? Okay. The only reason why we are doing this is to really make it efficient. That's the whole idea. So if you think about it, let's say your loss function depends on 3 independent variables, A, B, and C. I'm just taking, okay. You can imagine that there are weights and losses and the output from the previous layers as well, but let's not confuse ourselves. Let's just keep it simple. Your loss function has 3 independent variables, A, B, and C, and it's defined by C multiplied by A plus 2B. It could be as different, as difficult, as complex as you want, but for the sake of simplicity, let's say our loss function is C multiplied by A plus 2B. Okay? So, what are these functions here? If you are looking at C multiplied by A plus 2B, underlying calculations are this one, 2 multiplied by B, let's call it D, then A plus D, and then C multiplied by E. So this whole thing is E, this is D, right? Those are the computations that are happening here. Correct? Basically, you can take any function of, doesn't matter how many independent variable, and convert it into a computation graph. Does that make sense? Right? If you have converted into a computation graph, a forward path will let you compute the loss function. So, if that is a loss function and inputs are 3, 1, and minus 2, in the forward pass, you can actually calculate what the loss function value is. That should be very simple to understand. Is that correct? Yeah? Now let's say the loss function is telling us of negative 10, because whatever, we're not going by what the loss function is or how we reach there, that's what it is. We are trying to minimize this. Now we need a backward pass to adjust these values. How do we do that? What's the backward pass is doing? Now we require, what calculations do we require? We require the partial derivative of loss function with respect to A, with respect to B, and with respect to C, because there are three independent variables in our loss function. So far so good? We just talked about partial derivative. Partial derivative L over A tells us how much a small change in A affects L. That's what we're doing. Now, the importance of the computation graph comes from the backward pass. This is, if you ask me, one simple reason of where we are with large language models today is because of backpropagation. Because Geoffrey Hinton in early 2000 figured out that backpropagation can be used to do the adjustment of the weights, because that's what the learning is. It improves the learning. So what we are doing here, if you think about it, by picking an appropriate loss function and using a computation graph which does at each node a very simple arithmetic, we have converted calculation of partial derivative to some simple calculations. That's what we have done. That's the beauty of this backpropagation algorithm. So now what is going on, if you compute these partial derivatives, and again the chain rule is repeated here, fx is, if it is u of v of x, then df of dx is du dv dv dx. We all know it, but we'll see how this chain rule is implemented or captured in this computation graph. Same way, if you have a 3 u of v of w of x, 3 nested function, you could compute. Now let's call is what's the partial derivative L of with respect to C if the function is above there? Can someone tell me if you know the basic calculus differentiation? The function L is defined by C, A plus 2B. Partial derivative of L with respect to C will be what? Right. It will be the function E, which is A plus 2B, obviously, right? Let's calculate both A and B. What will be the partial derivative of L with respect to A? Yeah? So you calculate the same way. A is part of E, so you would calculate partial derivative L with E over A. E is broken down in D and B. Eventually, if you solve it, this is what you end up being. The partial derivative of L over C is E. E is A plus D. D over dA is 1. D over D is 2. So D is equal to 2B. This ends up being 2. This is obvious here too. A is 1 and C is E, which is A plus B. So basically what we are doing here is, when we are doing a backward pass, we are very simply calculating these numbers of partial differentiation and figuring out what the weights will be. This is the calculation if you think about it. Very simple example. You can work through by hand by changing the loss function slightly and then see how exactly it's going on. Given this, you can figure out what the values would be for partial derivatives going back. Now, from this, which is a very simple example for intuition, to the actual implementation, there's a lot more detail, right? But then you got to understand what we have as a very simple intuition about how exactly these things are functioning. Okay, all right. So the backward differentiation on a two-layer network. What we had an example of just one layer network. Now this is, again, we're trying to introduce some complexity here, but again, keep in mind, it's just the intuition that I want you to have. Okay, so if we continue on a two-layer network, you basically start from this first one, and then now you have a ReLU activation, two different activation functions. So what we are saying here, that this hidden layer has a different activation function compared to the output layer, which is a sigmoid activation, which is giving us a scalar answer, yes or no, or a binary answer. Okay? If you look into the maths there, you start with same formula that we said. The output there is applied to a ReLU activation, and then you apply the same formula again, which then goes to a sigmoid activation, and then finally you have the result. So think about it. If someone gives you a description of a neural network layer in terms of each layer, which would be in terms of the activation function, you should be able to intuitively understand what is going on. So if I have to tell you the description of this neural network layer, it say takes an input of 2 values, 2 layers. Hidden layer has ReLU activation and the output layer has sigmoid activation. You should very easily get it. Okay, it looks like a classification network layer. Because what's going on? Your answer is giving you a single binary answer. Yes or no, in or out. So you should very clearly get it. If someone tells you instead of this place that the output layer is a softmax layer, what does that tell you? Right. So your output would be probabilistic inference, basically. 1 out of 10 will have, you'll have probabilities for 10 different options or 100 different options or whatever the case may be, right? So basically you're learning about a description of a network and how exactly you are going to interpret that. So if we continue about that, if you are trying to do the same partial differentiation options here, and I'm not going to go into the math, the slide will be there, you can work it through yourself. Basically, what we are saying is a 2-layer network of a backward differentiation. Now, all of these things are for intuition. Understand this. When you are coding them, they will look very differently. I could have shown you the code, but it will be very difficult to get the intuition. Basically, what is happening is that whatever functions we chose, we create a computation network, and then we do a forward path and a backward path by calculating the partial derivatives at each point, and then calculate and use them to activate. I'm not going to go into all this detail here, but if you figure it out, you will see that because our loss function is based on a cross entropy loss, the calculations are really very simple. And I'm not going into all these details here. 3 things are happening here: partial derivatives, the chain rule of multiple functions for differentiation, and that's exactly what we're doing. I'm not going into the detail of all of this math. Let's just get to this point here. Why computation graphs? I did give you a hint about this because it's all about the performance. And then what is happening here, if you think about it, the derivative of the loss with respect to weights in the early layers, you could compute it at the very end and apply it in a single shot all the time. This is exactly what we are doing. We can automatically compute. This part is, so if you think about it, as I mentioned earlier, initially we were talking about whether the neurons can do it, the layers can do it. This is purely from the efficiency perspective, to make the learning faster, quicker, and effective. Effective part comes from the differentiation. We know that because we are trying to find the rate of change and apply the negative of it. Because we want the network to be really big, then we want it to be efficient as well. Okay, those of you who are inclined to go through the math, go through this on your own. You'll find it how exactly it's working. I don't want to basically spend time in going over the entire math here, but this is what it is: backward differentiation, efficiency aspect of it. Okay. Any question? If you want to walk me, if you want me to walk you through the entire math, we can do that. But if that's what most of you want, but it's a simple, basic calculus. 2 things: partial derivatives and the chain rule. Those 2 things have been used, and obviously the logarithmic function.
When we just for what propagation? For what propagation?
Yeah.
So why we want want to do a backward propagation. What is the
Connected.
Okay. All right. Anyone wants to answer this question, because we have covered this. Why do we need back propagation, right? That's your question.
Yes, sir.
Yeah.
Because we want to mitigate the differences which are getting at the end of the output. Why gap?
Right. So we are trying to mitigate the loss function. What is loss function? Loss function is difference between the observed value versus desired value. So we want to minimize that value. To minimize that value, we need to adjust our weights and biases. And you adjust the weight and biases by finding out the rate of change. Right? So the back propagation, so what is going on is that you can compute, so if you have a multiple layers, you can only compute the loss at the very end. Once you've computed the loss, then you are doing the partial derivative and applying it backward. And then again do the feed forward, and then again compute, and you have to do this learning in multiple cycles till you minimize the loss function. Right? If you try this out on the AND and OR and exclusive OR examples by hand, you will realize this. Okay? So I have already given the exact weights and biases which will implement those functions. Don't use that as a starting point. Use something different. Then you will see that you would figure out that, okay, my output is not matching. Then you adjust them, and then you will figure out how exactly intuitively you learn this. Okay? All right. Anybody else? Question? Yes.
What is actually the bias and why we are inputting it at every layer, at every hidden layer?
Okay. So I think this was asked earlier as well, like what's the reason behind it? So if you think about it, I gave you two intuitive answers. One is obviously there is no, so okay, you are here in discovery phase basically, right? If somebody, so let's say, I gave the same example of projectile here, right? If instead of projectile you can say something else. So let me just ask you this question. We have a value, we have a gravity, right? How is the gravity represented? Now I'm going a little bit in physics here. G. What is G? No, there's a value number here.
9.8?
9.8, right? Why 9.8? What is the scientific reason? Right. So basically you observed some behavior, and then somebody says that there is a force, which is gravity being applied. And then it was discovered that value of 9.8 captures it. Right? So the same way we started with a neuron, we said that the intuition that we had was from the neuroscientists. They were saying that the neuron in our brains are nothing but adding the inputs. Then we realized that it's not simply adding the inputs, they are adding inputs with different weights. So we added the weights. Then the researchers realized that just the weights are not sufficient, because if you make it in such a way that the output is 0, because we want zeros and ones, there will be a time that entire input, the entire network will produce output as 0. So they said, let's introduce a term called bias. So intuitively I can tell you that it is avoiding getting to a point where your entire network is producing the output as 0. Right? Okay. Now, if it has come in here, let me just introduce. Has anyone heard this term called right? This became a problem. What happened is that you do the calculation and all weights suddenly become 0. Right? This happened. So all of these things are learning. That's where they introduce a bias term, saying that let's try to avoid that your network becoming all zeros all the time. So we are trying, I can't give you the answer, give me a scientific, there is no scientific answer. The G could have been 9.3, but then that's the observation, it became 9.8. So the functioning of the neuron basically says that there are weights and there are biases, and both of these are learned as part of learning exercise. That's where the current research stands. We will see if it holds or if it changes. Any other question? Okay. Why don't we do this? We're just going to do a quick understanding of deep learning, and then we will stop after that, okay? Again, intuitively, there's enough of math. Hopefully I'll try to avoid going math, but I'll say that just hand calculate a few of those things and then we'll figure out. So if you basically introduce more and more hidden layers, we end up what we called as deep learning. Deep learning is simply saying that your neural network has more than one hidden layers. That's what it is. Input layer is not counted. If you have no hidden layer, you have a one layer network. If you have, in this case, like two hidden layers, so you have 3-layer network here. Basic calculations remain same. Every node is doing exact same calculation. The only thing that are different is weights and biases, and the thing could be different is the activation function. Each layer is named traditionally by the name of the activation function that it is using. So you might see that softmax layer or a sigmoid layer or any of those things. If you know what the output layer, what the activation function for the output layer is, that you get good feeling of what the output is, classification or probabilistic inference or whatever the case might be, right? I've covered most of this thing. Multi-class classification basically means the probabilities or a softmax layer here. Restricted Boltzmann machine, this was one of the early implementations of trying to build machine learning. I've included it here primarily to give you a historical viewpoint. Also, what it is used nowadays for pre-training. Let's say, what would pre-training mean? What would pre-training means? There's also a related term called transfer learning. What would the pre-training or transfer learning mean? So if the learning is finding out the weights and biases, if you are always starting with no learning at all, or like a standard zeros and ones for weights and biases, that's no learning. But if somebody gives you a pre-trained model with some initial or starting point for weights and biases, that you have a pre-trained model that you can use to modify. The RBM or the restricted Boltzmann machines are generally used for pre-training a model that you can then multiply. Also for transfer learning, in the sense that, and again, all of these are research areas. You learn the weights and biases for one application and then use them to apply into a different use case by transferring the same amount of weights and biases and also the structure of the network. Alright, so in the deep learning, now we're going to look into very quickly a few different type of networks. Some of you probably may have heard about it, CNNs or convolutional neural networks. Those were the very earliest ones. The reason they were used for, when you write a mail, right? I don't know how many of you are still dropping the letters, but still being used there. Early 2000, almost 2020, actually, this is going even further, probably like 30 years ago. US Postal Service was looking for a solution to automatically scan the address, handwritten addresses, and then figure out what the address is and then automatically route. This is, I think, in 1980s. That's when the convolutional neural networks were discovered to interpret the handwritten addresses and convert it into automatic routing mechanism. So basically, those things were trying to learn the handwriting symbols, especially the numbers 1, 2, 3, 4, 5. And once they get this will be. This is a very specialized kind of neural network. It's used for data grid-like topology. So each number was represented, I think, in 5 by 9 or 9 by 5. I'm forgetting the exact dimensions. So you represent it there, and basically this was used for interpreting the handwritten numerals. So for example, if you are writing 5, it will be this. So you break it down in grids and then train a neural network to identify a handwritten number by saying this, what number it is. So let me ask you this. What would be the output layer? Does it have it here? Okay, it's not. Sorry? Who said it? What would be the output layer?
Softmax.
Right. Because it's not a classification, it's discovering from 0 to 9 what the number is, so the output would be a softmax layer, exactly. So if you continue with this, that's what it's doing basically. This becomes an idea where you were doing the parameter sharing, equivalent representation, a lot of different things starting from there using a convolutional layer. Now what is a convolution layer doing here? We haven't talked about that. I mean, we will be going into a little bit detail here of the convolution layer. I think we have it here. Yeah, we have it here. So one difference that is happening here is that instead of working into a vector, it is working in a grid. So up until now, see, we're going a slightly more complex. Our input was a vector, right? 1 to n. For this example, it will be an array, right? What's going to happen there is now you have to discover features in a two-dimensional array. A convolutional layer basically try to discover features, something like whoever was doing here detection of the buildings and things like that. That's a very similar kind of a case here, that you have a grid and you're trying to discover features. The convolutional layer, basically what it is doing is that it's trying to learn features. The way it does is that it runs a small window over the input image and try to identify what exactly is there a feature or not. So for example here, okay, I'm not sure we have it. So it would run a smaller window of, let's say, 3 by 3 and then say, is there something of interest? And the learning basically becomes is that, okay, if I find something like this, this is of interest for me. That's what happens. A typical CNN or convolutional layer network will have the alternating convolution and pooling layers, which would basically be kind of learning or finding features into it. Okay, what the convolutional layer does, there are a couple of different functions that they are using. So literally what you are doing is that you have original image and you have a smaller grid which is actually getting shifted one row, one column at a time, and then it is combining the two functions, the convolution functions or a cross relation functions or autocorrelation functions, all of this based on the research. Depending on your exact use case, you may find that one function is doing better than the other function. So literally what is happening is, your end goal is to discover what the number in here. Instead of doing it, because you can't do it, you take a subsampling of each of this and say, this is of interest. Or I'm learning that there's something here. It could be 5, it could be 3, it could be 7, something of that nature. All of this is intuition. We don't know exactly how these things are functioning, but they're trying to discover features. You got to figure out which function, what combination works for you better. There are a lot of published research which says for this problem, this works better. For this problem, this works better. Okay? We are a few more things. All right. So that's exactly what we are doing here, in the sense that you're trying to figure out or identify features by localizing this, and this is what is happening in convolution layer. If someone has done electronics, this is basically filtering as well, if you're trying to understand this. And what we are doing here, if you think about it, slightly different from the other one. Here what we are doing is that we are taking a higher dimensional input and trying to reduce it into a smaller dimension for better identification of features. So that's what is happening. Subsampling reduces the number of parameters that you're working with and basically trying to give the likelihood of a feature in the whatever the window that we have. Then we combine this, and in general a CNN will look like something like this. So you start with a number which was actually a 28 by 28, then you let it run through a couple of different, and this has not come out, this is my problem here. So you have a kernel which is a 5 by 5 window which gets all over it, and then it reduces the size and then basically combine those layers multiple times and eventually get into a softmax, which gives you a possibility of 0 to 9, which one it is. I can give the reference of this image. This also is from a published paper. So you could figure out what exactly is happening here, a combination of convolution and pooling layer, which basically determines the features that you are in interest and eventually going into a softmax function. Make sense? So convolutional neural network, why they're important? Because they're the earliest ones which were being used, very effective in doing this kind of exercises, which is basically identifying features which are of interest in a grid-like function. The other example that we are going to keep coming back to is called generative adversarial network, or GAN. This is behind what we know today about the large language models. Roughly what is happening here is that there are two models working in tandem. One is generating an output. The second one is computing how likely that this output is from the same distribution that you originally used. So in a way, it's trying to confirm that it is right or not right. Whatever we talked about 2 days ago about deepfake actually came from here, because you can now create a fake which is as good as the same. What's going on is that they're saying that you take the audio sample of someone, let it go through this GAN network, and this will generate a fake, continue to refine it till it matches with what the original was, right? Unfortunately, that's a bad situation to be in. That's what the technology is doing. But the bottom line is same if you think about it, what is going on here. What we are saying here is that the input is coming from some known function. It's all functions all about. So this is a known function. So let's call it f known. The generator is generating an output from this distribution, and then the discriminator is checking this, that how likely it is that this one came out from this function. So keep in mind, this is not a supervised learning here. This is unsupervised that is happening. Generator generates something, discriminator computes a possibility or probability that this did come from the same distribution function. If it finds a difference, the generator generates another one by incorporating the feedback, and eventually you kind of, both of these things agree that now the output is exactly what this will generate. That's how the deepfakes were generated, but this is one way of producing the output. We will see the example of this generative adversarial network in the context of large language model as we continue to go about. So this is what generally it does, is that this is the random distribution, generate a network, and then the discriminator will tell you this is exactly same or not, and then it will keep on giving you the boundaries, the classification error, and then you try to reduce the classification error. That's how the generative adversarial network models work. Can someone give me an example of how they work in the large language models? Has anyone tried, let's say, writing like Shakespeare? So if you ask a large language model to say, write me a story as if Shakespeare is writing it, and you get some more input, what is it doing? It's using the original function as the Shakespeare writing style. You don't control what it is. You assume that the network knows it. Then it generates an output, and then it matches with that style, yes, no, and then that's how it basically is using. So partly it's learning, partly it's yours telling it what to do. Okay, so intuitively we saw three different type of networks: the convolutional, the actually two, GAN. We didn't talk about autoencoders, but we will look into it later. Any questions here at this point of time?
Connected.
So we assume it's not written as functions.
This Shakespeare writing style is not written function, and we are trying. So it generate that function or first, or it's already
No,
predestined.
no, not the function basically. So we are assuming that the base model, the foundation model, the large language model knows about Shakespeare's writing style.
It should know first.
Yes, that's the assumption that it knows about it.
Okay. It cannot generate its own.
Okay, so I'm not going to use those terms
Yeah.
because no one has explicitly told it what it is. It has actually generated of its own. By doing what? By giving the supervised learning, saying that here's a Merchant of Venice written by Shakespeare. So it has consumed all the works of Shakespeare, right? That's part of learning. Now nobody told it what exactly that model is. Assumption here is that the model knows if Shakespeare would have written it, how it would sound,
Okay.
right?
One more thing. According to that, we are going to the world. Like human have a predictive. Like he has some feature. Example: how his moves, how sees, how facial expression shows gesture.
Yeah, yeah.
So can we predict, like if I'm sitting in a station, the camera is focusing on me right now, and we are doing some artificial intelligence using some artificial. Can we guess what he's going to do? Like he is criminal, he has an intention to do something crime
Right.
after 10 minutes, after 10 seconds, like this
Okay.
great prediction. You
Hold on to that thought. That's a week 2 kind of thing. So you're saying that can there be a system trained to keep a look at this class
Yeah.
and then say that this person is not paying attention to this, he's watching the Instagram, right? That's what you're saying roughly.
Future prediction.
Yes,
Like-
or the current prediction, because can you find out or not? Hold on to that thought next week. I mean, the answer is yes. Is it happening 100% correct? Maybe not. So we'll talk about those things when we go into the use cases and ethics of doing certain things.
Okay.
And then, is it right to, or let's put it this way, can we trust the machine to predict it? So for example, let's say I had this secret camera here, which is doing exactly what you're doing, and it is telling me here that this person is not paying attention, she's studying something else, or Facebook, or looking at some whatever that you guys do in social media. Should I trust that system to punish you for not paying attention in my class? It's a similar example, right? Or the law enforcement agency is monitoring people visiting in Kumbh and something that this guy is acting suspiciously. Let's just arrest him. So theoretically, the answer is yes. Does the technology exist? Yes. Can we trust the technology? That's where the question is, as it stands today. So we're going to get into those areas next week. Okay? All right. Any other question? Yeah.
Sir, can CNN learns the graphical sketches?
The graphical.
Sketches like,
Yes.
like a medical images and anything.
So, okay, the two separate parts here.
Yes.
Can it learn a graphical image? The answer is yes. If you take it, the medical imagery, the variant of the CNNs have been used for that.
Yes.
So think about it, as I said earlier, depending on the problem that you're trying to solve, you have to find out which is the right function, what's the right architecture, and what the right weights and biases, that's all. So a variation of CNN has been used.
Okay.
Yeah, if you go into the research, you will find that, let's say for computer-assisted tomography or for X-rays, what kind of models have been used to interpret them.
I think, sir, electrocardiography.
Electrocardiography, there are a lot of different ways. So there are different inputs that you can provide, and you can use that. Yes.
Okay, yes.
Okay. Any other question? Okay. I think we're going to stop that here today. And then when we start tomorrow, we will now are, I think, ready to go into the language models, which is the basic idea of generative AI. So what we will do is that we'll start with a language model. I'm not adding large to it. We'll start with giving a basic understanding of what the language model does. and then we will go on to large language models and things like that. Okay? All right, great. Thank you.
Thank you very much. Still, we have some time. Okay? Just quarter to two till, we can continue till. Yes, so in between, if you would like to have your lines.
That would be perfect. Thank you.
So I'll finish within 10 minutes time, okay? So yesterday we had a discussion that we need to know about applications of artificial intelligence. So I have a thought about it, okay? So today, he talked about some facial detection, then crime, and then lot of creative applications we have started thinking about, okay? So you need to also think about what application, okay? So quickly, if I conduct a survey, I wish to conduct a survey, and then maybe I'll get back to you, okay? इसको connect कर देना. ये नहीं जाएगा बेटा, ये आराम से इधर. आराम से ऐसे ही. हाँ, ठीक है, मुझे दे दो. Just to make you familiar with this survey tool, okay, मेरा इंटरनेट जरा कनेक्ट करना है इससे. इसका पासवर्ड मालूम है? इसका पासवर्ड कोई बता दीजिए जरा, आपको मालूम जी.
स्मॉल ए आई आर is IR 877.
कनेक्टिंग बोल रहा है. ओके,
एयरटेल ये लीजिए EIR 87752.